Consider this 3D figure. It's a solid. All right. Consider trying to find the volume of this figure. One approach we can do is to think of one of the edges as a function. Maybe this edge. How can this work? I'll show you. So, if this is our vertical axis and that's our horizontal axis. And then we think of that edge as a function that starts at A and ends at B. So this is the point A, this is B. Now we have the edge. I colored it green, like this. All right. So this is the graph of a function. This is the graph of a function y equals f of x. All right. Now, consider rotating this function from A to B across the x-axis. If you do that, you will see that you're going to end up with this particular figure. So you have your figure again. Over here. So this is your x-axis. So we have a graph and we looked at a region, call this region R, and then we rotate the region. And after rotating the region, we got a solid. Our goal is to find the volume of this solid. Okay? We want to find the volume. Let the volume be V. One approach we're going to take is to slice up our solid. Let's get a slice of our solid. Before I do that, maybe I should make this a little bigger. All right, so I'm going to do this. Okay, maybe like this. Okay, so what we can now do is to get a slice of our solid. So what do I mean? We could go here, get a green slice on this part. Okay, so get a slice, a very tiny slice. So if we get this slice, we end up with maybe a circle, a disc actually, because it's going to have a thickness. The thickness of the disc is going to be, let's call it delta x. Okay, so we have a disc. We would like to find the volume of this disc. But now look at this. we want the radius of the disk. That's the radius. That's all we need to find the volume. Because if we find the radius, we can find the area, and then we just multiply by delta x, because it's a very tiny disk. Okay, so let's look for the radius. The radius, we slice this out at this point x. So if you go over here and you try to figure out x, the height of x, which is the same thing as the radius, is just f of x. So this radius is actually f of x. Okay. So this tiny little disk, its volume is delta x. Sorry, it's pi r squared. Pi radius squared times the thickness, delta x. So it's actually pi f of x squared delta x. Okay. So, but the volume we're interested in finding is the volume of our disk, of our solid V. So to find the volume of this solid, we just have to integrate the volume of these little disks. Each of these disks, the thickness is delta x. So if we can integrate a bunch of little disks from A to B, then we find the volume of our solid. So you can say, therefore, volume of solid V is the integral from A to B of each of these little volumes, pi f of x squared, but then the dx, we can just change it to delta x now. Okay. So this is what we're going to be dealing with. All right, this is almost like a formula, but I would warn you not to think of this as a formula, not to use this formula. Each problem I give you, I would expect you to think through the problem. Think through it each time, and make sure you get your little slice, your disk, and then find the volume. Okay, so this method we just described is called the disk method, and there are other methods like the washer method, and you see why this is called the disk method and the other methods are called the washer method. All right, so let's look at examples. So this is for the disk method. So our first example is we would like to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals f of x from x equal to 0 to x equals a. So again, we now know the setup. All we have to do is visualize it properly. So we have this. We have the curve. y equals square root of x. And then we rotate this curve about the x-axis, and we're going from 0, x equals to 0 to x equals 1, and we rotate it about the x-axis. After rotating it, we get something like this. So we're looking for this volume. That's the volume we're looking at. So what did we do before? We got a slice of the solid, a little slice of the solid, like this. All right, what did we do with this slice? We looked for the volume, but in this case, let's actually just look for the area, because the volume, think of the volume before was just the area, which is the area of a circle, pi r squared times delta x. So it maybe makes things a little easier to just think of the area, which is pi r squared. So all we need to look for is the r. But if you think of this, the r in this case is our function. This is the radius. Because if you are at x over here, your height is going to be square root of x. And that's the radius here. So that's square root of x. So that's the area. Let's think of the area. Remember I said volume before, but let's just think in terms of area. The area here is going to be pi r squared, but your r in this case is square root of x squared. Okay? So all you need to do is to integrate these little areas from 0 to 1. Add them up, stack them up from 0 to 1, and you get the volume V. You get your V. Okay? All right. So we start with the integral. So the volume is the integral from 0 to 1 of pi square root of x squared. So this is your area, and then you throw in the dx, but the delta x, but we now change it to dx. Okay, so think about this. This is the integral from 0 to 1. X squared, square root of x squared is just x, and we factor out the pi. Right, dx. So this integral, factor out pi, you have x squared over 2. And then you're going from 0 to 1. So this is going to give you 1/2 pi. So that is your volume. All right. How about if we want to find the volume when we rotate about the y-axis? So let's look at this. So we want to find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. All right, so how do we want to do this? So first of all, let's look at all the curves that were mentioned, all the functions that were mentioned. So we have, start with our y-axis and our x-axis. So we have the line, or we have the curve y equals x cubed. So maybe I should use another color, maybe a lighter. So this is y equals x cubed. Y equals x cubed. And then you have y equals 8. And then you have x equal to 0. So x equals 0 is the y-axis. So because that's where x is equal to 0. This is x equals 0. So this is the region we're talking about. This green region. All right. So all we have to do now is rotate this region about the y-axis. This is our y-axis. Rotate, and this is our x-axis. Rotate it about the y-axis, and then see the figure that we get, the 3D figure that we get. So let's do that. Thanks. All right, so this is what we're gonna get, right? After rotating. And we're going from 0 to 8 on the y-axis. So what do? We get a little slice like before. And we find the area of this slice. So this slice is a disc. It's thick, but let's just ignore the thickness at this point. So we want the radius to find the area. But now look at this radius. Look at this curve. This curve is y is equal to x cubed. But I'm going to rewrite it as x. We can also write it as x is equal to the cube root of y. Why am I doing it this way? Because we want to find the radius. And the radius here is some x over here. Okay? And this x is dependent on a value y. This x is the cube root of y. Since we are rotating about the y-axis, it will make sense to integrate along the y-axis, to integrate from 0 to 8 along the y-axis dy. So we want our function to be in terms of y. So that's why I'm doing that. So this now, our radius is the cube root of y. So with that, this volume over here, volume of this disk is pi r squared. The r is cube root of y squared. So we're looking for a volume, this volume. So the volume now is going to be the integral from 0 to 8 of pi r squared dx. But our r squared is the cube root of y squared dy. Sorry, I said dx. All right, if we work on this, we factor out the pi. We're going from 0 to 8. And then we end up with y to the power of 2/3 dy. I will let you finish this integration But if you do it correctly, I think the answer should be 96 pi over 5. I want you to check my answer and tell me in class if it's correct or not. All right. Now I want to challenge you. I want you to prove something for me. I want you to show that the volume of a sphere of radius r is 4 over 3 pi r cubed. All right, I'll start it for you. If you think of a sphere, you might see a sphere as a semicircle with radius r that is rotated about the x-axis. So this is a semicircle. Well, let's make it really semicircle. So like this. Oh. I think this is better. So center the semicircle at the center of the x-axis. So this would be r, and let's make this negative r. Okay? So remember the equation of a circle. The equation of a circle is x squared plus y squared is equal to r squared. So if you solve for y, this would give you that y is the square root plus or minus the square root of r squared minus x squared. Okay? So we only need one of these functions. We don't need both of them. So we take the top one, and the top one is y equals square root of plus square root of r squared minus x squared. So the next thing we do is we rotate around about the x-axis. So if we do this, we rotate about the x-axis. So we, oh no, we get something like, no, I'll get it right. We just get a circle that we're going to turn to a sphere. So this is a sphere. So all you have to do now is to cut out a slice. Cut out a slice of this sphere at a point x. Remember, this is our x-axis and that's our y-axis. So cut out the slice. Now I want you to look for the area of this slice, surface area, or you can think of it as the volume if you multiply by dx. So what's the radius, etc. So you now set it up. You now do everything as we did. Your v is going to be from negative r to r, and you put something in there, dx. And then you show me that this volume is equal to that 4 pi r cubed. Okay. So that's for you to try. Now let's look at another kind of figure, another kind of solid figure. Remember that we found or we kind of formulated the volume of our solid as revolving the curve of a function about the x-axis or about the y-axis, like in the second example. Now think about this. How about if we now have two functions? Think about the case where we have two functions. I'll show you what I mean. So if we have so we have this function over here. Oh no, I don't. We have this as f of x like we had before. And then we have another function, g of x. So this is f of x, y equals f of x, and this is g of x. And we integrate or we rotate this region, make it green. We rotate this region from A to B across the x-axis. Now, what do we get? Picture what we're gonna get. You know, I want you to draw what we get, and then I'm gonna draw mine, and let's see if it matches. Okay, don't look at mine. All right, so don't listen to me, don't look at mine, just do yours. Do your thing, let me do my thing, and then we compare. All right, so we have this. Okay. That's, oh, this is messing up. This is F, and this is G. And when we rotate, we get that and that, okay? So we get something that looks like this. All right. Yep. So we get this hollow figure. It's hollow. This is the x-axis. So this side is thick. It's solid. So this is the solid part. All right. And then we have a hollow part. All right. So what we're going to do now is we're going to try to do the same approach. We're going to get a slice, a green slice again. So think about getting a slice of this solid like this, cutting it from here. All right, when you do that, what do you end up with? You end up with this. There's gonna be a hole, kind of like a donut, but it's commonly called a washer. It's not a donut. It's commonly called a washer. Well, think of it as a donut. Now, it's like a hollow circle to concentric circle, and we're looking for the area in between them. So from here, the area out the radius of the larger circle is f of x. The radius of the inner circle is g of x. All right. So that means that if you're looking for the volume or the area of this little slice that you cut out, the area is going to be the area of the larger circle, which is pi r, no, sorry. Your r here is f of x, pi r squared, area of larger circle, minus the area of the smaller circle, pi r squared, but your r here is g of x. Okay, so you can think of this as pi f of x squared minus g of x squared, all right? And then if you want the volume of this solid, the volume now is going to be the integral from a to b of pi f of x squared minus g of x squared dx. Again, I would want you to not think of this as a formula, to think of it as something you arrived at after setting up the problem. Okay, so this is commonly called a washer. So we're going to call the examples we're going to do here, we're going to call them the washer method. So let's look at examples. Number 1. So this is the washer method. Okay, so the region R, is bounded by the graphs f of x equals square root of x and g of x is equal to x squared between x equal to 0 and x is equal to 1. The question here is, what is the volume of the solid that results when R is revolved about the x-axis. Okay, so this is one of my favorite problems whenever I teach Calc 2. I don't know why. Maybe because of the figure. So you have y is the square, f of x is the square root of x. The function looks like this. Call it y. And then you have g of x. So let's say f of x. And then you have g of x is x squared. And you have this region R. And then you're rotating this region about the x-axis. Okay? So what do you get if you rotate about the x-axis? You will get something like this. Oh no. I'm struggling with this. Give me some time. Okay, so you get this figure. All right. So you can think of getting a slice over here. Like that. These two functions, they intersect at the point x equals 1. Okay. So this is 1. So we get a slice. But now, the slice is no longer a disk, it's a washer. All right? The radius of the inner function is x squared. So we have this as x squared, the inner function. So if you go from here to here, if this is your x, and you go from here to here, this is just x squared. And we're taking the slice at the point x. And then the radius of the outer function is this function. That's square root of x. So we're going to call this square root of x. So again, I want you to think of just finding the area of this figure. All right. In actuality, it's better to think of it as the volume and multiply by delta x, but it just makes things easier if we think of the area. So the area is equal to the area of the larger circle minus the area of the smaller circle. Area of the larger circle is pi r squared, but the r here is square root of x squared. The area of the bigger circle is pi r squared. The r is x squared squared. And then we're looking for the volume of this solid figure. This is solid here. The volume. So our volume, V, is the integral from 0 to 1. Remember, this wasn't explicitly stated in the problem, but they intersect at 1. You can prove this by just setting x squared equals to square root of x and showing that it's in the two graphs intersect at 1. So we're going from 0 to 1 of pi, the area dx, pi, square root of x squared minus pi, x squared squared dx, right? Let's do a little bit of this. If you factor out, you can actually factor out a pi. You'll be left with 0 to 1 of x minus x to the 4th dx. All right, if you keep going and you do this integration, you're going to end up with 3 pi over 10. I want you to try it. Okay. You know what? Let me do a little bit of how we ended up at x minus x to the power of 4. I'm going to bring this down. I'm going to go over here. So this is integral from 0 to 1. I'm going to factor out a pi, and then I'm left with square root of x squared minus x squared squared dx. So I can now bring out the pi. If I bring out the pi, then I have 0 to 1. Just square root of x squared minus x squared. And that's how I ended up there. And I'm sure you can do this integration to get the correct answer. Let's do one more and let's end there. I want you to find the volume of the solid generated by the region R, by by revolving the region R about the y-axis. The y-axis this time. All right. Here, R is the region bounded by y equals 3x, y equals x, and y equals 9. I'm going to sketch it for you. This is y equals 3x. The slope is larger than y equals x. So y equals x, y equals 3x. And then you want to go to y equals 9. Y equals 9. So let's use a lighter color. So this is y equals 9. Okay. So this is the region. This is your region R. That's your region R. And you're rotating R about the y-axis. You're rotating R about the y-axis. Okay. So your integration has to be in terms of y. So you have to rewrite a bunch of things. But you don't even have to. You only have to rewrite this particular one a little bit. Okay. Your integration has to be in terms of y. So I want you to try it and tell me the answer you get. Or maybe let me try it with you. So if you rotate, you end up with this. So this is solid. This is all solid. All right. So you get a slice around here. Get the slice. And this slice, you're getting it around y. All right. I'm going to make everything a little larger. Make this larger. I always find out that it's better to start out large. Making it larger doesn't always give me what I want, but it's better than nothing. So this is my x-axis, and that's my y-axis. So I'm taking this slice at y, okay? So this, I can write this function. I can say that this function is y equals 3x, or x is equal to 1/3 of y. That's what I'm going to say. So if I take my slice, this green slice, what does it become? It become a disc on the floor. If you put it on the floor, become a disc. It has an inner radius and an outer radius. The inner radius is 3x, as you can see. The outer radius is x. And then you find its area. All right? Inner radius 3x, outer radius x. But now, think about this. We want to integrate along the y-axis from 0 to 9. So it's better to think of our stuff in terms of y. So I'm going to erase this. I'm going to write what it should be in terms of y. So the outer radius, 3x, y equals 3x, but along the y-axis, the outer radius is, or along the x-axis, the outer radius is actually x is equal to 1/3 y. So that's what I'm going to do. No, the inner radius. I am sorry, I'm messing things up. So this is the inner radius, and this is the outer radius. So this inner radius, it's x is 1/3 y, and then this outer radius is just going to be y. Okay, so the area, this area of this little thing is equal to the area of the outer circle, the larger circle, which is pi y squared, minus the area of the inner circle, which is 1/3 pi 1/3 y squared. All right, so we're looking for a volume. Don't forget that. This is the volume we're looking for. The volume V is now the integral from 0 to 9 of the outer area, which is pi y squared, minus the inner area, which is pi 1/9 y squared. Where did I get that from? 1/3 squared is 1/9. All right, and then dy. If you do this integration well, if you do it well, you end up with 216 pi. That's what I got. Check my answer. All right, we're going to stop there. This is a very long video, but I have no choice.